All right, so the first problem we are going to tackle is converting an NFA into a DFA. And we're going to use a definition of an NFA that's just defined by this set of transitions. And this will hopefully help us to be able to read such transition notation, because I think one problem on the new homework also is from this same problem set. So take a few minutes, work with some neighbors, and see if we can get started. We'll go over this in pieces over the next few minutes. So I would say step one would be draw the NFA. Draw the NFA defined by these transitions, and then start going through the NFA to DFA process. And do note that all slides are available on Canvas. So even if I have this up right now, you can go refer to that slide deck while you are working if you'd like to. I'll probably switch back over to it once we draw the NFA.
And is it just by assumption that Q2 is the final state?
Yeah,
Sorry.
Q0 is the initial state and Q2 is the final state. Do we have an NFA yet? Raise your hand if you have an NFA for this so far. Couple people. We'll start drawing it out. Where do I want to draw it? Because I want to keep this where I can switch the slides. Maybe up here. No, it doesn't want this. Over here. All right, so on Q0, we can read an A, either Q0 or Q1. So Q0 will loop to itself on an A and also transition to Q1 on an A. From Q1, reading a B, we can get to either Q1 or Q2. On Q2, reading an A, we can stay in Q2, and then Q2 is our final state. So this is our NFA. That's what all of those transitions define in terms of a state machine. Hopefully you had something similar to this. But now the question is, we want to convert this into a DFA. Do we remember what that process was?
Terms, like, don't you first find the non-distinguishable or non-reachable?
That would be if we were reducing the DFA to the smallest possible DFA. This is the NFA to DFA conversion. So we have some number of subsets of potential states. The reason we keep these really small is because there's potentially 2 to the power of the number of states here that represent subsets of these states. So let's bring up the slide with the algorithm. Oh, I didn't override my diagram. Look at that, that's basically perfectly placed. I'm proud of myself now. All right, so we had the intuition, then we had the example that we had here. So we first figured out what the initial state of the DFA was going to be. The initial state of the DFA was going to be anywhere you could reach from the initial state without consuming any characters. So that means look for any lambda transitions. There were no lambda transitions in this built NFA. So we don't need to worry about it. The starting state of our resulting DFA is just going to be Q0. I guess let's start building an associated DFA. Now we're going to start here. From Q0, reading an A, where do we end up? Could be Q1. Could be Q0. So we need to make a new state from Q0 that's going to be what would be a hybrid state in the NFA. It's going to be Q0, Q1. And remember that this name can be any possible subset of the states in the NFA, which is why there are 2 to the power of the number of states in the NFA, possible states in the DFA. Not saying we're going to use them all. What happens on Q0 reading a B? Because this needs to be a total function in a DFA. An NFA does not have to specify certain transitions. What happens, or what does it mean if we don't specify a transition in an NFA?
It just rejects it.
It needs to fail. Yeah, so we need to define a trap state. So we're going to define this trap state out here that's going to be the null state that loops to itself on an A or a B, and this transition will be on a B. I forgot one question here. Is Q0, Q1 a final state?
No.
No, why?
Neither are defined as a final state?
Yeah, that's exactly right. If at least one of these states in this subset is a final state, then the result will be a final state. But since neither Q0 nor Q1 are final, then this Q0, Q1 is not final. All right, now we need to figure out transitions in and out of this Q0, Q1 state. So from Q0 or Q1, if I read an A, where do we end up? Where could we end up? What are the possible sets of states starting in either Q0 or Q1? It could either be, if we're in Q0, we could be in Q0. If we're in Q0, we could be in Q1. If we're in Q1, we have to go to the trap state. Or basically, there's no way to accept from Q1. So the possible sets of states are Q0 and Q1. You can think of this as empty. We only transition here if it is empty. So this tells us that we will loop Q0, Q1 to itself. From Q0, Q1, reading a B, where could we possibly end up?
From Q0 to 1.
Yeah, from either Q0 or Q1. So we want to define this B transition out of Q0, Q1, which requires us to refer back to the NFA and say from either Q0 or Q1, what is the set of states that we could reach reading a B?
Q1, Q2.
Yeah, if we're in Q1, we can loop to Q1. If we're in Q1, we can go to Q2. So we're going to define a transition from Q0, Q1, reading a B that gets us to a new state called Q1, Q2.
And it's the final state.
Yes, because Q2 is a final state, then Q1, Q2 is a final state. What is the intuition behind that? Why does that make sense that we declare this as a final state? It's not just the statement that one or more of these were final states. What's the intuition behind why, if one or more of these states is final, then we make that associated state final?
Has it met the same condition?
Yeah, but basically there is a way to get to a final state in the NFA, which is how we define acceptance in the NFA world anyway. So yes, there are ways that you can navigate A followed by a bunch of A's and a B, A, B, that leads to a non-final state in this. But because there exists a way to get to a final state, the NFA would have accepted, which means that the DFA needs to accept. And basically, this is saying that any path that could get to here, you could reach Q2 in some string, or with that string in some possible configuration of that NFA. You can get here with AB, you can get there with AB. You can loop any number of A's, so you could have one A before the AB, AB, you can get to a final state, so AB needs to get you to a final state. It gives you the equivalent language. All right, so we need states out of Q1, Q2. So from Q1, Q2, what happens if we read an A? Where could we end up?
So.
Is there any way to get to? Yeah, it's only Q2, because there's no way from either Q1 or Q2 reading an A to get to Q1. So that is a separate subset of states than before. So we need to define a new transition on an A that only gets to Q2. And this is going to be final because Q2 is final. What happens if we're in either Q1 or Q2 and read a B?
Just. That's it.
If we're in Q1 and read a B, we can get to either Q1 or Q2. If we're in Q2 and read a B, we fail. So from here, we need to define the B out of this state in order for it to be total. So B will loop to itself. Because you can get to Q1, we're going Q1 reading a B, and you can get to Q2, Q1 reading a B. So that is the subset of states you can reach from Q1, Q2 reading a B.
But you're asking just about Q2.
Now I'm asking just about Q2. I said Q1, Q2 before, so it makes sense that Q2 reading a B, there's no way to do it. So that goes to the trap state. And reading an A, it goes to itself. So that should be the whole DFA. Do we agree that this is a DFA? Does it conform to all of the rules of a DFA? Is it a total function? Are there no possible states where there are multiple defined transitions on a single character in the alphabet?
How do we handle, in the NFA, we consume an A to go from 0 to 1? How do we handle, what do we mean to at all, if we consume an A at Q1?
We don't need to worry about that because there exists a path to a final state.
Okay,
So you don't define the transition before you read, you think of it like a tree. Where if we wanted to read the string A, B, then how is this NFA going to do this? Well, we're gonna start, we know we're in Q0. We could stay in Q0 reading this first A, or we could transition to Q1. So we're kind of gonna draw two children in this tree, one of which is Q0, one of which is Q1, to show us the options that we had. Okay, reading the second A, if we're in Q0, we could either stay in Q0 or transition to Q1. So this is on reading the first A. This is on reading the second A. I guess better would be to do this at level order. That's reading the first A. This is reading the second A. We could end up in Q0 or Q1. If we're in Q1 and read an A, we're in the trap state. There's no way out of it. So this is just going to die right here.
okay,
And then you would continue this process to say, all right, for the third A, for all paths that are open so far, where do we reach? From Q0, we could be in either, this is A3 now. Could be in Q0 or Q1. And from Q1, we go to nothing, reading this A. So now we need to read the B. If we're in Q0, we can't read the B. So this dies, but from Q1, we can read a B, and we could either be in, this is the first B. We could be in Q1 or we could be in Q2. And now we ask, is there a path through this tree from the root to a leaf where the leaf is a final state?
okay,
So this would be the process of deterministically going through the NFA. But the whole point of the NFA is to be able to do this non-deterministically. That basically says, if there is a path through this, we're going to accept it. And the idea would be we don't have to fully explore it. If someone gave us a path and said, validate whether or not this path through this NFA accepts or rejects this string, then you could do that in linear time without having to draw out this tree, which in worst case, in this has a branching factor of the size of the alphabet. If that makes sense, the worst we could do is break this and say on an A or on a B. Like, so I guess it's a number of characters in the alphabet times the number of possible states out. So this could have a maximum branching factor of 4. Although on an NFA, I guess that could be even worse. It could go to every possible state. There's no bound on the branching factor for these trees, which is why we don't do it deterministically, because it explodes exponentially based on the depth of the tree and the possible branching factor. So it's gross.
I think you answered the question, but, at Q0, in the NFA, if we take a B, it would go to a trap state, so we made the trap state in the DFA, and we would transition to if we took a B.
Right.
If we go to, in the NFA again, take the A to go to Q1, and then we take another A, that would lead to another trap state, wouldn't it?
If we had done that, but it's just one of the possibilities of this NFA. So the NFA is gonna say, if there's a possible path, then we will accept. So in that case, the first A would stay in Q0.
Yeah.
And then the second A would transition to Q1 in order to handle those two A's. So yes, you would consider going there first, deterministically, if we were trying to answer that question. But remember that non-deterministically, the question we're answering is basically, if we're given the path that is the final state, how long does it take us to validate that the string is in the language?
Okay, thank you.
Excellent question. I think that really hopefully helps to show the difference between what a DFA is needed to do. The DFA needs to have this complexity kind of built into it. because you can only be in one particular state after reading an A. After being in Q0 and reading an A, you are in this state, and there is no question about it. In this NFA, if you're in Q0 and read an A, you don't know what state you're in. You're in either Q0 or Q1. And if you're in a deterministic world, you have to kind of try to figure out, am I in 0 or 1 at this particular point? Non-deterministically, it's just if it's possible to reach a final state, which allows us to make much simpler diagrams that represent the same language. Questions on this problem? Questions on the process of converting an NFA to a DFA? So that is the process you will go through. Kind of figure out what the starting state is, and then just start making this a total function state by state. And you may need to create states that are subsets of these states to be able to resolve the non-determinism. All right, next one is also pulled out of one of these homework batches. So when I upload this, there will also be a solution. Here is a solution. I think that's what I drew. All right, 2.4. This is problem 3. I think I assigned A, C, and D, so I just wanted to do B and E. Just so that we had some additional ideas going into this problem set on the homework. So we need to find minimal DFAs for each of these languages. So in order to provide a minimal DFA, we need to first draw some DFA, solve the problem somehow, and then go through the process of converting the DFA that you come up with into a minimal DFA. So going through that algorithmic process of reducing the number of states and determining whether or not they are distinguishable or indistinguishable. So let's start with B. A to the n B, where n is greater than or equal to 1, union B to the n A, n is greater than or equal to 1. So intuitively, the first thing that I want to do is come up with some strings that are in the language, just to help me visualize what this union actually means. So if we were representing the left-hand side of this language, what are some strings in A to the n B where n is greater than or equal to 1?
Ab,
Ab,
put as many A's there as you'd like.
yes. AB, AAB, AAAB, AAAAB, etc. So we did this. This would be the left-hand side. We want to union that with the right-hand side. What are some strings that are in B to the n A and is greater than or equal to 1? Ba. What else?
Oh, it's multiple.
Ba-ba. Ba-ba-ba. Ba-ba-ba-ba. Etc. All right. So if we can union these two sets together, we will have the language to accept. So we need some DFA that's going to accept either something in this or something in this. You made it.
Finally.
Stupid weather.
I'm just more like, this is my phone today. I'm like, well. And
So we did a practice problem. Here that just converted an NFA to a DFA. So there's an answer on the slide. There's also the working through of that that'll be on the recording that I post to YouTube later today. So we're currently working on 3. I assigned A, C, and D for homework. So we're gonna do B and E in class, just so people know how to do these kinds of problems. So the first thing that I did for B, which is the union of A to the N B and B to the N A, was to just think about these languages and start writing some strings in them. So intuitively, A to the N B, where N is greater than or equal to 1. We start with AB, and we recognize there can be any number of those A's preceding that single B. So AB, AAB, AAA, B, AAA, and then union with the right-hand side, which would be the NA, so that's BA, BBA, BBBA, etc. So now that I've written out some strings and what those look like, I feel like I am ready to process and derive some DFA. Once you derive some DFA, you're going to want to go through that process of determining indistinguishable versus distinguishable pairs, so that you can figure out if the DFA that you came up with is the smallest possible DFA. Brownie points if you come up with that smallest DFA from the first get-go. That's always the challenge. You don't think they have a DFA yet? Couple people? How many states are in your DFAs?
6 count start with 6.
6? Do either of you want to come up and draw your answer on the board? I'm actually really happy that it is 6, because that is not the minimal DFA. But I want something that's not the minimal DFA, so that when we go through this process, we can see some indistinguishable pairs so that we can combine them.
You can come up, I guess.
Yeah. If you're feeling so inclined. If it is, who's judging? It's a learning effort. So the minimal DFA here does have 5 states, but that doesn't mean that there aren't a plethora of other DFAs out there that have more states that are still perfectly correct. This is like saying you implemented an algorithm, but the algorithm wasn't 100% efficient, but it still produces all the appropriate outputs for the same inputs. So it's the same algorithm, it's just slower.
Slowly down.
Yeah, I think that's right. Excellent. Thank you. All right. Is this similar to what people were working on? Does this look reasonable? Let's take a gander through this DFA and think about whether or not this solves this particular language. So we start in Q0, and on the left-hand side, we read some number of A's before a single B that tells us that we've finished the string. So we start at Q0. We need to see at least 1A, right? So we can't combine Q0 and Q1 probably, because we need to see at least one of these A's. If we were to just do this and see a single A without that loop, or if we put the loop on Q0, then that would accept some weird things for the right-hand side. So we need to kind of split out the left-hand side, which Dominic has drawn here on the kind of top, and the right-hand side that has been drawn on the bottom. All right, so we have some number of A's. We can loop Q1 as many times as we want. As soon as we see a B, we transition to a final state. This is everything we've seen so far is in the language if it stopped right now. But there are quite a few strings like AAABA or AAABB that wouldn't be in the language, that get to a point where they are in the language, but then there's more stuff. And it's unfortunate that that more stuff exists, because it means the string's not in the language anymore. So that's why we transition from this final state on any character, it doesn't matter what, to a trap state. Similarly, on the bottom path, we're looking for at least 1B. It's the exact opposite of this. We look for exactly 1B. We can loop on a bunch of B's in Q2. Doesn't matter how many of them we see until we see a single A. Then we transition to a final state, and that needs to be the end of the string. If there's anything else after that in the string, trap state, not in the language. Do people buy that this DFA solves this problem? I do.
Yeah.
I think it's correct. The question is it minimal? So to do that, we need to divide these into some number of classes, basically. And we're going to start doing it by finality. So we are going to ask ourselves, all right, which of these states are non-final? So we have Q0, Q1 is non-final, Q2 is non-final, and the null trap state is non-final. The other one is going to be our list of finals. I don't know what happened to Q3, but it disappeared. We have Q4 and we have Q5. Doesn't really matter what they're called. So these are our, we're just gonna call these non-final states. We're gonna call these final states. So I'm gonna bring up the slides that walk us through this process so that we can kind of see it as we go through it. Somewhere on this screen, there is a mouse. There you are. Let's start here. This was for a completely different problem, but it walked us through the process. So let's get rid of this so people can read this text. All right, so first is asking, are there any inaccessible states? And Dominic drew us a very nice DFA without inaccessible states. So we could go through that process of iterating all simple paths through this graph to determine if there was some node that we couldn't get to, but I think we can all see that all nodes can be reached. So next, we split the states into equivalence classes, already done. Now we need to start looking at pairs and reading every character in the sequence. So we're going to look at, let's start with some non-final states, Q0 and Q1. We want to figure out if these are separate states. So now the question is, if we read a character from Q0 and read a character from Q1, do we end up in states with the same finality for every possible character? So from Q0, Q1, reading an A, we end up in Q1 regardless, and Q1 is non-final. So this looks fine on reading an A. Q0 and Q1, reading a B. We transition to Q2 and Q5. Q2 is non-final, but Q5 is final. This says that these states are distinguishable, and we can pull one of them out of this. We'll pull Q0 out, and we'll make a new class that only contains Q0. We could then look at Q1 and Q2. All right, so in Q1 and Q2, if we read an A, we transition to Q1 and Q4. Q1 is non-final and Q4 is final. So we found the difference in these. So these are in separate classes. So we can pull one of them out. Q2 and the trap state. You will find that you will very rarely have to do this with trap states, unless you're looking at trap state and trap state. It's very possible that you could create two trap states. And it's pretty easy to see that if you start in a trap state, you're going to end up in a trap state. The issue is, unless that trap state is, one of them is final and one of them is non-final. So in this case, we can see Q2, the intelligent one to use here is an A, because the idea is to make the transitions different in some capacity. So we look at Q0 and we look at the null state, and we see that if we read an A here, we'll end up in a final state, and if we read an A here, we'll end up in a non-final state. So that tells us that these are in separate classes. So we need all of these states. So now we have completely split apart our non-final states into sets of just one state apiece. Given that I said the minimal DFA has 5 states, that means that Q4 and Q5 should be indistinguishable. Let's see if that is true. We go from Q4 and Q5, transition on an A, we go to the same place. Transition to a B, we go to the same place. This means we can combine these states into a single state. So how we could do this is I'll make a new final state called Q4, Q5. And instead of transitioning to Q5 on a B, we will take a detour and go down here. And instead of transitioning to Q4 on an A, we'll take a detour and go here. An A and a B will transition from here out to here. And this means that we can eliminate this state. Since there's nothing going into it anymore, it's inaccessible. And we can eliminate this state because it is inaccessible. So this process found a way to do this. And said these are the same. So now we know for sure these are the same, and you can combine them. We want to continue this process until we make no changes. So we will loop back around, but you can see now that there is a single state in each class. When that is the case, you will terminate. Does that process make sense? You're going to take a DFA of size 6 and turn it into a DFA of size 5 by finding those indistinguishable states. Questions on the process? You want to try one more of these? We have 7 minutes. We could get started with one more of these. There's one other type of problem I can start tomorrow's class with. Let's go back to our practice. Yes, let's do problem E. So I'm going to give a little bit less guidance at the start, and I'm hoping that in addition to creating the DFA, we can actually go through the DFA reduction on our own or in pairs. Go through the whole process now that it's been guided, and we'll see what we can come up with. So the left-hand side now is a to the n, where n mod 3 is 1, union a to the n mod 5 is 1. What are some examples of strings on the left-hand side?
A.
Mhm.
For A's, A to the 4th.
What else? Right-hand side, n mod 5 is 1.
In this assumption here, there's only A's in the language.
Correct. It's going to make terminating distinguishable or indistinguishable interesting, because we only have to consider transitions on A's before we make a decision. Who has a DFA at this point? It's like nobody. Good. How many states did your DFA have? 15 states? How do you feel about there being 15 states in that DFA? Do you feel like, think it can be reduced? Interesting, let's start going through that process and see if we can reduce a 15-state DFA. And I agree that the intuitive way to construct this is a 15-state DFA. Now, the interesting intuition for people is, do you feel like there is a better solution than 15 states? Intuitively. Now we have the tools to be able to prove it. Are technically out of time. I know this is a thrilling problem. My task for all of you is to work on this a little bit between today's class and tomorrow's class. We'll come back and talk about the solution first thing tomorrow, and then move on to one final kind of practice problem from the regular expressions that we've been talking about. I did post homework 2, so homework 2 is up. It has stuff through regular expressions, because that's assuming that we were doing practice problems today and some of tomorrow. That's as far as I figured we'd get by Friday. So the homework is slightly smaller than last time, but I still recommend getting started on it early, because as we all know, roadblocks happen, and it's nice to have access to office hours that don't have 20 people in them to get those questions answered. If you start early, you're gonna have individual time with either Harlan, the TA, or me to get your questions answered. We'll see you all tomorrow. Questions?
When we're comparing like, if we got a current statements, so they're saying like, okay, when we got them with A, are we looking at what state they go to, or the finality of the state they go to?
The finality of the state. Yeah. We should be completely caught up aside from these practice problems. And then I think this is actually in the homework, so you could refer to the problem in the homework in order to, I don't quite want to post it, because as you can see here, I have a solution to the first problem. The next one will be the solution to the second problem. So I'll post them out there tomorrow.
Oh,